Yeah. So I spent most of my time with
Good afternoon, everyone. Can you guys hear me? It says 1:49 on the clock here, but I think we're at time. I think there are a fair number of people circling in, but we have a lot to talk about, a lot of things to do this afternoon. So we're going to go ahead and get started. I'm Greg Kirk, Vice Dean for Research here at the school, and we're very excited for our second annual AI Research Day, and that people are continuing to be very interested and engaged with public health and AI strategic endeavors, or the PHAISE initiative, which we launched in February of 2024. And I think at that time, most of us probably would foresee that AI would have an integral role in public health and also in the education and research activities of the school. But I'm not sure we truly envision just how much AI seems to be commonplace. You just can't avoid AI in almost any area of your daily life. At that time, we did a survey, and I hadn't planned to do this, but I think I want to resurvey the crowd. At that time, we had substantial heterogeneity. A third said they were AI aficionados. They'd been doing machine learning for a long time and did foundational work. A third said they were AI eager, that they could see how they could leverage AI to incorporate into their research or teaching. And another third were AI skeptics. They were hesitant about the biases and equity involved with AI, and that perhaps it was more hype than it might actually turn out to be. So let's just do the non-AI. We don't have any polling. For how many would you consider yourselves an AI aficionado? All right, all right. How about you're AI eager? That's pretty close. Okay, AI skeptics, go ahead, raise your hand. All right, Scott Zeger's an AI skeptic, everyone. You heard it here first. So I think that the proportions, my informal count suggests that perhaps we're becoming a little more receptive to incorporating AI in our explorations, our analysis, and our applications. Before we get to the keynote, I want to say a few thank yous. And the first is to our PHAISE task force. PHAISE has representation from all the different departments as well as staff and students, and it's intended to connect the BSPH community around public health and AI, providing links to AI-related resources, sponsoring intensive sessions on AI and public health topics, and hopefully increasing collaboration among our investigators internally as well as outside of the school. So this is the current task force membership. And if you're here, raise your hand. Please join me in thanking the PHAISE task force. I'd also like to thank Dean Ellen McKenzie, who was supportive of us launching this PHAISE task force, and to Dean Keisha Pollock-Porter for her continued support. And with that, I'd like to ask Keisha to come up and share a few comments.
Thank you, Greg. Good afternoon, everyone. Thank you for responding. It's a great pleasure to be with all of you today for our second AI Research Day, sponsored by PHAISE. And I really want to applaud Greg, and thanks for his leadership. Since launching PHAISE 2 years ago, PHAISE has initiated vital, in-depth discussions within our community, helping us to identify areas of strategic interest and need. And it's given us an opportunity to bring leading experts to our campus. At our first AI Research Day, we had Dr. Ziad Obermeyer join us from UC Berkeley, and he spoke about machine learning and how machine learning can help doctors make better decisions and help researchers make new discoveries. And I was in attendance that day, and I remember all the energy that was in the room and the excitement. And today I'm thrilled we're hosting yet another engaging and inspiring speaker, this time Jeff Leek, who I know many of you remember. Jeff is a former Bloomberg School faculty member who also served as co-director of the Johns Hopkins Data Science Lab, and today he's chief data officer at the Fred Hutch Cancer Center. He's a biostatistician, an entrepreneur, and a true leader and innovator in data science. And Greg will tell us more about Jeff in a moment. But one of the things that I love about Jeff in describing his work, he said that he builds things to help people, which is something we all can get behind. So I'll just say a couple of things before I turn it back to Greg. Certainly we know how important data are in the field of public health and for our school. You know, we use analytics all the time to prepare and measure impacts of health and disease and illnesses, including preparing for the next pandemic. We research trends in human behavior to address everything from smoking to HIV prevention. We use evidence to study and improve health policy, which is my area of expertise. And we know that having better data and the ability to unlock what those data mean are the first step towards understanding the root causes of poor population health and how we as a society can address those root causes. With AI, we now have an extraordinary ability to use data in powerful new ways to improve public health discovery and practice. In other words, there's a lot at stake for our work and for the world based on what we're talking about today. And while the intersection of AI and public health can be a challenging space, I believe it's a challenge that we were made for and that we are ready for. AI at its heart and public health at its heart, with these two intersecting areas, is a powerful combination of data-driven solutions and deep commitment to addressing and finding solutions to help those most in need. I'm so proud of the groundbreaking work that we're doing here. In the past few years, we've launched multiple courses to provide cutting-edge training on how to use AI effectively and ethically, with diverse offerings for both our students and for non-degree, non-credit learners. We also have researchers who are using AI to advance suicide prevention, study wastewater, track long COVID symptoms, and so much more. And this is only the beginning. There's so much work still ahead and so much for all of us to learn, which is again why I'm so thrilled that we have Jeff here today. So I want to note that following today's keynote, we will continue the conversation by recognizing 3 investigators for their outstanding abstracts, and there'll be 30 posters featuring AI projects on display in Feinstone. So I invite you all to head on up there to come check them out with us. So with that, I want to turn back over to Greg and just say how thrilled I am for our speaker today. So thank you so much, Greg.
Thanks very much, Keisha, for those encouraging AI perspective. And as Keisha mentioned, our speaker has come to us from a cross-country journey to be here today from Seattle. But previously, you would find him here at the school in the biostats department. He completed his PhD in biostatistics at the University of Washington before making that first journey over to Baltimore and joining the Hopkins faculty, where he was recognized for his methodologic acumen as well as his entrepreneurial spirit. He was pretty rapidly promoted through the ranks to professor, and during his academic success during 13 years at Hopkins, he was never really just an academic-focused faculty member, but he was always doing other things. He helped to build data science capacity in the school as co-director of the Johns Hopkins Data Science Lab. He helped launch the JHU Data Science Specialization, or MOOC, massive online open courses where millions of individuals have received training in data science and AI skills. He also leveraged this type of work to start Data Trails, which was to tailor coursework for young people in East Baltimore to perhaps develop a career path in data science. Jeff was recruited back to the West Coast about 4 years ago to become the chief data officer and a professor of biostatistics at the Fred Hutch Cancer Center. At the Hutch, as everyone calls it, he oversees data science analytics, infrastructure, security for both the hospital and the academic enterprise. Again, never just an academic. He also has developed the nonprofit Cancer AI Alliance, a groundbreaking platform that leverages a federated AI framework to aggregate data across cutting-edge cancer centers. He also co-founded Synthesize Bio, a generative genomics company, which is using AI models to model how human tissues or cells can respond to medicines or disease, and hopefully to develop new medicines. And just within the last few days, Jeff, I understand that GeekWire nominated this first generation model from Synthesize Bio as the AI Innovation of the Year. So you can check that out and perhaps give him a few extra votes. I'm not sure when voting closes. I like that. Okay. So with that background as a biostatician, a data scientist, an innovator, and an entrepreneur, please join me in welcoming Jeff Leek.
All right, first we see if I can figure out how to run the computer before I talk about AI for 30 minutes. All right, here we go. So first of all, I want to say thank you very much, Greg, for the invitation to come back, and Dean Pollock-Porter, Junie, Sarah, for organizing this and making it possible. This has been an incredible gift to come back. Everyone should have the opportunity to go away from a place that they loved and people that they loved and then come back and see those people again. It's been a day filled with seeing people in the halls, giving hugs, getting excited about things we used to get excited about together. And so it's been an incredible gift to be back here with you today. And thanks everybody for coming out. Greg asked me to really focus on the sort of the relationship or the intersection between AI and public health. And this is a topic that I've thought about a lot in all of the capacities that I've been interested in this area. And so I was going to talk a little bit about this idea of inference with predicted data. And really the kind of way I've been thinking about it is, in the future, machine learning is going to eat more and more of what we do. AI is going to eat more and more of what we do. What do we do then as a public health enterprise once that's happened? I usually am a walker around, so can you hear me if I like shout, or is that going to get recorded, or do I need to stand there?
I think we're recording.
Okay.
So
so stand here. I'll be stationary.
sorry.
No worries. So first I have to do a couple of conflict of interest, because as Greg pointed out, I co-founded this company. I also teach these Coursera courses, which generate revenue both here and at Fred Hutch Cancer Center. So again, so excited to be here. This is how I felt when I got the invitation and how I felt all day today. It's great to see all of you. I'm going to go predictably very fast through these slides. So if you want to see any of the things that I've talked about, you can go to this website and look for talks and find these slides later to peruse at your leisure. So this is kind of what I thought I'd talk about today. So first is, everybody talks about AI, and everybody has a slightly different definition of AI. So it's helpful, I think, to kind of make it concrete about what I mean by AI when I talk about it, and why I think now is the moment that everybody's so excited about it. Then there's this really interesting concept that really some colleagues of mine are about to publish a paper on, treating AI as an exposure to an infection, and how does that kind of how should we think about using AI when you kind of think about it in that context. Then talk a little bit about how now is the moment and why machine learning is touching every aspect of public health, and how do you do public health once the data becomes data generated with AI. And then I'll kind of conclude with some thoughts about treating the exposure more broadly. So again, I'm going to go fast, so you got to hold on because I'm going to go quick. So first, what is AI and why now? So when I think about AI, so in my role as the Chief Data Officer at Fred Hutch, I often have to explain what is AI to people that I'm talking to. And I think of it as every AI has three components. It has a data source that it's being trained on. It has a model or an algorithm that takes that data source and produces some output. And it has an interface that lets you interact with it. And the third piece is kind of what makes AI AI, in the sense that for a chatbot, the famous interface with ChatGPT, where you can type some text in and it spits some stuff back out at you. But another example of AI is cars that have adaptive lane control and stay in. They're turning the steering wheel. That's the interface. They have a data model and they have an algorithm behind it. Now, this can be as complicated as something like this, where you have models with trillions of parameters. It can also be something as simple as just a simple linear regression model with a shiny interface on the front of it. In my opinion, that's still AI, because you're using an algorithm and humans are interacting with it. So why is everybody talking about AI? It's because there's two revolutions happening at the exact same time. One is you can rent more and more computers on the internet. This was easy for a while. Now it's getting very hard to rent computers on the internet, but for a while it was quite easy. And at the same time, the cost of collecting data is dropping dramatically. And so this is my area where I've worked for a long time in genomics, but you can make this same graph for imaging or electronic health record data or wearable computing data or really any type of data, environmental health data. So I'm not going to put too many formulae in this talk, but one I will, courtesy our own Ingo Rosinski, is a famous sample size calculation. So if n is your sample size, the sample size calculation is the number of dollars you have divided by the number of samples, dollars per sample to collect, is how big your sample size will be. And so one of the things, again, not making you do too much math, if the denominator goes to 0, this number gets very big in a hurry. And so we've seen that explosion of data because the denominator is essentially going to 0. So that's why we're having this moment in time. Another reason is people like me, but also people around here, are developing open source software that make it easier and easier to do things with that data. Many of those folks are in the audience here today. One piece of software we're working on is a piece of software that lets you fit these complex deep learning networks, including the transformer architecture and such, but doing it in R with very simple amounts of code. And so we've built these systems where you can write R code and then fit these very complicated models on like cloud computing on big data sets. And so you can take what is quite complicated code to build a diffusion model, which will generate dinosaurs for you from random noise. The Python code is quite long. The Scorcher R code can be very short and just a few lines of code that you can kind of interpret very much like the tidyverse does for other kinds of data. And so we're one of the groups making models like this, open source software like this. This is Steve Salerno's work. He's a postdoc in my group, but lots of other people are. And so it's all happening. Like at the same time, you have the data that's coming together, it's getting cheaper, you have the computing, you have software, you can do it. And so everything is happening all at once. And it's been called the Cambrian explosion of AI. And so AI is kind of like an exposure that's happening to all of us. This is actually slide courtesy Steve, but these are the folks that are writing this paper. It's actually not out yet, so I'm semi-scooping them. But it is rapidly spreading through both the scientific and general communities. It is influencing public health research, public health practice, our own health, our own environments, our own mental health. So it has the capacity to do good or the capacity to do harm, but it is like an infection in that way, and that people get exposed to it and then they start using it. And I really like that model. And when you think about it in that model, it's perhaps the most infectious exposure that has ever existed. So in just 2 months, ChatGPT went from 0 users to 100 million users, which is unbelievable. And if you go and look at the number of people that use these tools regularly, it's measured in the hundreds of millions. For both, any of the really top tools are being used by hundreds of millions of people around the world on a pretty regular basis to do everything from asking about helping them code, to asking about their health, to using it as a therapist. So it's all of those things at once. And so machine learning there's that excitement that happened with those large language models, but it's really now applying to everything else. So a large language model is really just a predictive algorithm that takes text as input and predicts text as output, and it's just trained on an enormous amount of text and a very complicated model. But we do this all over public health. So I'm just going to show a couple of examples here. So if you want to get a good map of socioeconomic status across the United States, one way that people have tried to do that is by using Google Street View. So they use Google Street View and they predict socioeconomic status. Now, this does well in some places, poorly in other places. It has a set of operating characteristics, but it is a dramatically cheaper way to measure this kind of characteristic that we would want to measure at scale. Another example is being able to forecast child malnutrition and do early warning. And so if you use sort of high frequency sort of monitoring, that you can use data to essentially predict when there's going to be outbreaks of malnutrition. And so that's another example where we're predicting a set of data about how the world is going to work, where there are going to be pockets of malnutrition from an algorithm. A third example is poverty, is combining satellite imagery and machine learning to predict poverty across the world, not just in the United States. And so they use nighttime lighting as a measure, as a proxy for poverty. And so like they would look at pictures at night of the world and they would say where there's a lot of light, there was less poverty, and where there was not very much light, there was more poverty. Again, none of these are perfect models, but they are models that people are starting to use to try to make these predictions. And what they're actually generating is data. So in this case, this prediction is a set of data about the geography of poverty around the United States and around the world. And then you might use that to answer public health questions that you want to answer with that data. So another example is infectious disease monitoring with Google search engine data. If people are searching for cough a lot on Google, they can predict or not influenza outbreaks and other such outbreaks. And then the example that I'm going to talk a little bit more about today, which is verbal autopsy, which is we've been working on this project with our collaborator, Tyler McCormick at the University of Washington and many others, where it can be expensive to do a full autopsy on people, especially in places where there aren't good facilities for doing that and they don't have the resources to do that. So they use something called a verbal autopsy where they ask about the symptoms of the person that passed away, and they use that to infer what the autopsy status was for that person. So they're making a prediction about the autopsy. So this is interesting because I had a similar problem in genomics that I was working on, and Tyler was actually visiting me here at the School of Public Health, and he was working on verbal autopsies. I was working on genomics, but it was the same problem, which is we're going to predict some data, and then we're going to try to do statistics with that as if it was observed data. And so this problem we called post-prediction inference. We now call it inference with predicted data. And increasingly, I think that this is going to be the way that a lot of public health is done. We have not just the data we collect in the old-fashioned way, so to speak, but also the data we generate with machine learning models. How do we do statistics? How do we do epidemiology? How do we actually study predicted data? And so in this example of verbal autopsies, you might ask yourself, the questions you actually care about is, how does cause of death vary by geography? Are there changes in time of those causes of death? What are the reasons for those underlying changes that you might see? And the way that you would answer those questions is with statistical and epidemiological models. But the challenge you have is we have predicted rather than observed cause of death for all of the verbal autopsy data that we have. And so we're doing statistics, but we're doing statistics with something we predicted from a different model. And so what happens when you do that? The other challenge is, if you want to figure out a way to manage this from a statistical perspective, is that these models can get unbelievably complex. It's quite straightforward if your model is, if they said fever, they died of the flu. That's something you can manage statistically. If your model is a $200 billion or 200 billion parameter large language model that's predicting your cause of death, it's a little harder to statistically model what's going on underneath the hood. And so you have to think about ways to address that problem that don't require you to do statistics on 100 billion parameter models. So in this case, the way that it works is you build these models. There's a couple of gold standards data sets, and they're often collected from around the world. And they might be trying to predict something like non-communicable versus communicable versus other kinds of diseases, maternal deaths, or in this case, AIDS is obviously, this is in certain countries, that's the common cause of death. And so you're building a model that essentially uses these verbal autopsy reports, uses natural language processing or now large language models, and predicts what did they actually die of. So that's sort of the underlying model that's generating the data. Then you have data on, in each country, what did people die of? And now you want to fit a statistical model across those countries to say, are there differences, for example? And so the data kind of looks like this. You have some data where you have the true cause of death, a verbal autopsy cause of death, which is a prediction, the age, country of origin, whatever else you want to model that relates to the cause of death. And then you have this questionnaire, which is what you're using to make the prediction of the cause of death in the verbal autopsy cause of death. But for many, many, many of the people, you don't actually have the true cause of death because you didn't actually do the autopsy on those people. You only have the verbal autopsy. And so for those people, you could just skip using that data. You don't have to go and try to use the data for all of those different people, but it feels like a waste. If you have verbal autopsies on 1 million people and only 1,000 people do you have real autopsies, it feels like a waste of data to not try to use that somehow. So this is the predicted data down there. So one way to do this is to just ignore everything except for the stuff you actually measured, which is the true cause of death and the variables you want to relate to true cause of death. Again, you're probably ignoring some of the data there. The other approach is to do what we call naive, which is what people have done kind of very often in this field, which is like pretend like it's all real data. Like forget about the fact that it's predicted. Why don't you just pretend it's all real and just fit your model that way? The challenge is if you use the predicted data as if it's real data, and then you fit a statistical model that relates, say, the country of origin to which kind of status of death that the person died of, you find that sometimes the yellow is the ground truth. Sorry about the colors here. Yellow is what's happened with real autopsies, the relationship between cause of death and location. The green is what happens if you do the naive analysis where you treat the predicted data like it's real. And often you will see that you might be off in the magnitude of the effect in that statistical model. You might also be off in the sign. You might get it completely backwards from what the actual relationship is to the true cause of death. So this is obviously not good, and you want to figure out a way to use those data, but use it in a way that makes sense. The robots aren't quite ready for prime time yet, and so how do we, for those AI skeptics in the audience, there's still some room for skepticism. And if you don't, this is Simone Gertz. If you take nothing from my talk, go watch Simone Gertz's YouTube channel. It's amazing. So we need inference with predicted data. And so the way that we originally thought about this problem, again, with a grad student in the biostatistic program at Johns Hopkins, was the first to come up with an idea for how to solve this problem. And so she worked on this problem, Sarah Wang, and she had this idea with Tyler and I of, okay, can we figure out a way to get around the fact that it's really complicated to model a large language model? What if we only looked at the outcomes? What if we modeled everything in outcome space? And could you fit a relationship between the true cause of death in the sort of training set and the predicted cause of death that would allow you to correct your inference later? And I'm not going to, just because I know you're not all statisticians, we're not going to go into all the details today, but there's a paper that Sarah wrote that's very nice on like how you actually use this relationship between the true cause of death and the predicted cause of death to correct your inference and try to get something that looks more like what you would have got if you had collected real data. And the kind of clever thing that she figured out is no matter how complicated the model you fit, so here she was predicting predicted values of y versus real values of y in a simulation. She uses k nearest neighbors here. But if you used support vector machines or random forests or neural networks, you still get this kind of quite simple relationship between the predicted outcomes and the observed outcomes. And with that quite simple model, you can extend, under some assumptions, you can extend and correct the inference in the broader population. So this is kind of a clever trick that she figured out. Since then, this area has become explosively hot. So in the statistics world, inclusive of a pure methods paper in Science around this idea of prediction-powered inference, but also lots of other people, Daniela Witten's group. There's a group out of Si-Hong Lin, and now just recently Brad Efron has a paper on it. So like this is kind of the area that a lot of people are thinking about since Sarah kind of came up with the first idea. And the cool thing is you can correct. So now I'm showing you that same graph I showed you a minute ago. You have the ground truth, you have the naive approach, and then you have this corrected approach. And if you do the corrected approach, you see that the purple and green dots, you have about the same estimate. The estimates are very close to each other. The ground truth and the corrected estimates are very close. You see that the purple confidence intervals are a little bit wider than they, yellow and purple, are closer to each other. You see that the purple confidence intervals are a little bit wider because there's no free lunch. So you got to like give up something to get this correction. And so this is an example of this. There are other people here who've done very similar ideas, including some folks sitting in the back in environmental health, like Avi and others, who've like also figured out this problem. This is kind of a common and important problem in the area. And the predictions don't even have to be that complex. So I'm showing you, we originally motivated this because the predictions are very complex and it's hard to actually model them, but you can actually do this and see that it has the same kind of impact in even quite simple problems. So if you're trying to look at the relationship between, say, age and obesity, you can define the sort of relation, you can define overweight by body mass index, you can define it by DEXA scan, you can define it by waist circumference. There's different ways. The sort of default gold standard is DEXA scan. And so if you're doing a relationship, you want to find a relationship between, say, age and being overweight or obese, you can measure height and weight, calculate a BMI, create BMI categories. That's a prediction that you've done right there, which you're trying to predict something like the DEXA scan score. And so you have these predictions that then you can use in downstream statistical models. And so if you go look at something like NHANES, you do have both BMI data, DEXA scan data, waist circumference, but you don't have DEXA scan on everybody. It's basically the same problem setup where you have the gold standard on a subset and you have the more commonly measured, cheaper measurements on a broader group. And you get the same problem, which is here I'm showing on the x-axis your BMI, on the y-axis you're showing the sort of DEXA SAN score on the left, and on the right it's waist circumference versus DEXA score. And so you can see that in both of these, there is a good relationship between waist circumference and the gold standard measurement. There's a good relationship between BMI and the gold standard measurement, but they're not perfect. And because of that lack of perfection, if you actually just use those measurements as if they were the truth, you end up with the same kind of problem. And so here you see basically the exact same thing, where here I'm doing the relationship between, I'm showing coefficients for the relationship between age and status, overweight, obese. And here you can see that in light blue and light purple with the triangles is the corrected version. All of the circles represent classical, which is the sort of gold standard, versus the naive approaches, which are the circles. And so I wish I could walk. Is there a way I can do oh man, I want to walk to point. Okay, here, can you all see that? Okay, great. So you can see that the naive approaches have really big coefficients here, and they have really big coefficients here. And then once you correct them to the triangles, they look closer to the gold standard, even though you're using BMI or waist circumference. So you kind of like can use the predicted measurements and get more power, but extend your sample size. And so this is another example of how these can be done. And so this doesn't just apply to really complex machine learning, really complex AI, kind of calling back to the beginning of the talk. My sort of definition of what is AI is quite a bit simpler. It's that it's a model, a data set, and an interface. That model might be quite simple. It might be, is your waist circumference above a certain number? It could be a model that's part of an AI model. And so in all of these examples, you can sort of see that there's ways to correct these sorts of things that allows us to use machine learning in combination with AI, or in combination with statistics and with public health, to answer the kinds of questions that we all care about by combining the best of both worlds. And so I think one of the things that has me most excited about the future of this field is that there's this deep complementarity to what's happening in the AI world and the machine learning world and what's happening in the public health world and the inferential world. And you can combine those two things together to really improve the way that we understand the way the world works. I think this is particularly important in light of, as we all know, there's a lot of challenges right now with our funding model, with the way that science is perceived. And so there's really interesting opportunities at this intersection that I think allow us to create excitement around a topic that is so important to so many people and intersects with the topic of, which is sort of AI. So the other thing I wanted to sort of briefly mention was to talk about this exposure more broadly. So AI is, as I sort of think about it, is an exposure that we all sort of feel about the way that the world works, whether that's happening in your personal life, whether it's happening in your professional life, and thinking about what does that exposure look like in a broader context. And so one of the things that has been a focus of sort of certainly my work, the data science lab when I was here, and many other people in the audience, Brian, Roger, other people as well, Jessica, who's in the back, has been going beyond just thinking about software, just thinking about statistics, to really thinking about generally how you think about treating an exposure like AI. And for me, I think that the way I really think about that is in light of a really broad focused approach to a really broad approach to thinking about the umbrella of things that you need to do when you're at the intersection of a brand new technology that has people thinking about how do I do things differently, how is the world changing, and the intersection of like a field that is got hard questions to answer that moves at a pace that's a lot different than the pace of the technology. So one of the things that I think has been challenging, I think, for everybody who's been at this intersection of AI and public health, medicine, et cetera, is that public health and medicine, for very good reasons, move much more methodically. They're much more careful. The answers to those questions are so important. We have to take them seriously, and we have to take the time to answer them well. At the same time, week to week, the AI world changes. And so those two timescales are very difficult to match up. And I think that it's not just about having a statistical algorithm that's better. It's not just about the people who are building those algorithms, but actually it's about the whole community. And so one of the things we've been thinking a lot about is for our practice, we have software, like I talked about at the beginning, like Scorcher, but also other kinds of open source software that enables lots of people to build models, not just the people who have deep expertise. I think this is critically important because a lot of what happens in our world today is being driven by algorithms. And it's important that many people participate in the development of those algorithms, not just the technical few. We've seen the negative consequences of only having the technical few be the ones creating algorithms. So it's very important to democratize the ways in which we do that. Another component of that is training. And I think training is very broadly defined. We were having a great conversation earlier today with Daniel Obeng, who's been thinking about how to integrate AI into courses here at the Johns Hopkins. Sorry, you can see me going to default. Here at Johns Hopkins, and he's actually, I think, doing some of the most creative, interesting work I've seen in that space. But I think in the future, there's going to be this complete intersection of AI and education. And I know that there are people that resist that and don't want it to happen, but I think back, I am old enough, believe it or not, to remember when Google got introduced. And so I very much remember when Google was being introduced and I was in an educational program, people were like, you can't use Google. Google is like this dangerous thing that like, well, like you'll never be able to do education well if people are using Google. It's cheating. It's all the same things you're hearing about AI now. Definitely, I remember sitting in classrooms hearing those exact same things about Google, where this is cheating. It's not allowed. It's going to ruin the minds of our children. And so I think that we need to think really broadly about what does it mean to engage with AI, because it's going to be part of our lives. Like one way or the other, it's going to be part of our lives. And so how do we think about engaging with it well? And, you know, the other thing that like really drives and motivates me in this way is my son, Dexter, is 14 years old and can already program and do things that I can't do with AI. And so if that's the kind of pace of the change that's going to happen to people who adopt these kind of technologies in a more deep way, we need to be prepared to help people understand how to interact with them. What are the pros? What are the cons? Another example is resources. So we had a great conversation earlier today as well about another component of my work and work around here too, which is in building data resources, doing data clean carry, and others were talking about this and talking about how do we actually build and Greg as well, build and sustain data resources that let people participate in and build AI on top of those resources. This is completely thankless work and is never funded by anybody that you want it to be funded by, but is the foundation for how all of these AI models get built. There's a kind of famous story. There's a really quite famous person in the AI space named Fei Li, if you've heard that name. Fei built something called ImageNet, and you may or may not have heard of ImageNet, but what ImageNet was that she just collected millions of images off the internet, and then she paid people to label those images. And she tried to get grants to do this and was soundly rejected by everybody. It was a terrible idea. You shouldn't do it. That collection of labeled images was the basis for basically the entire deep learning revolution. Like all of the methods that like now underpin all of large language models, all of that can kind of draw their path to the beginning of that one data resource that was made available so that everybody could build methods on top of it. And so this one's near and dear to my heart, not only because I spend a lot of time on it, but also because I feel like that's one where many people in the public health space are doing this, and it's such valuable, important work. And then methods, which again are underappreciated. I think that there's the early work that's been done at this intersection of statistics and machine learning, both by my group, but also by lots of other groups, I think is starting to set the stage for what the world's going to look like in the next 10 to 15 years. But what I'm really excited for is what we've seen is lots of grad students at lots of other places in biostatistics have really adopted not just this kind of model, but all sorts of models where they do the intersection of statistics and AI. And I think it's been really incredible to see how that works. And then finally, it's practice. It's really deploying these things into real practical examples. So this is a paper I didn't talk about here today, but there was a grad student, Eamon, who used to be here at Johns Hopkins. He's now working with me at Fred Hutch. He's a grad student at University of Washington. And he is studying the ways that large language models respond to patient questions. And he's doing that through the lens of expert rubrics defined by clinicians who then get applied, those rubrics get applied to evaluate how well large language models answer patient questions. And the kind of interesting result is that in some ways they do amazing things. They're very supportive. People tend to prefer the responses from these large language models. And in some ways, they're very dangerous. Like they can be range from bad to dangerous, where they might give you bad advice or dangerous advice. And sometimes they do great. And sort of understanding where that happens is, I think, an open public health problem. We were talking as well about how this applies in mental health, and thinking about how in the mental health space, when ChatGPT changed their model from, I think it was 4.0 to 5.0, there was a mental health crisis in the United States. And it was because the personality of 4.0 was different than the personality of 5.0. And people had really invested in building a relationship with 4.0 as their therapist, as a person they could talk to. And so when it changed, when the model changed, it really had an impact on mental health in the United States at a scale that's kind of surprising and shocking. And so these problems are here to stay. They're at scale. And I think it's really important for people in the space of public health to engage with them and to really help improve them, to study the ways that they work, to study the impacts they have on our world. Because in every discipline, environmental health, mental health, molecular biology, policy, these are all going to be affected by the ways that these models are implemented in the future. And so what made me so excited to come and give the talk here today, and really to be back at the School of Public Health, is how important the work of a place like the Bloomberg School of Public Health is going to be for the future of AI, and how critical it's going to be for that collaboration and intersection to happen with the technology changes we're seeing. So we can work with the machines. The robots can work together with us. And I think, in the future, we're going to see a lot more of that excitement and enthusiasm as this kind of field continues to develop. I just wanted to take a minute to thank all of the people that were involved in doing these different projects that I talked about here today, particularly Steve Salerno. For those that are paying attention to the bottom of my slides, like half my slides are borrowed from Steve Salerno. He's an absolute superstar postdoc who's on the job market, by the way. And anything good that you liked from this talk was from one of these people, and anything that was stupid or wrong was definitely my fault. So with that, I just really appreciate your attention, and thanks for coming.
Thanks very much, Jeff. Really appreciate that vision, the balanced vision. I think he touched on all three of those engagement scenarios: aficionado, engaging, and some skepticism as well. We're going to open it up for questions. I'm sure we have a few. I saw one hand go up weekly. Go ahead. We're going to use the microphones, Junie, so we can record. We'll bring you the mic. Here.
Hi, Jeff. My name is Nora. I'm a third-year PhD in biostat. So
Great.
I joined after you left, unfortunately. But thanks for the wonderful talk. I have a quick question about the resources and data collection you mentioned, like the ImageNet and also your resource collection. I was thinking, like, one problem for like public health or biomedicine field for AI is we don't have like a set solution. Like, for example, ImageNet, you can just label the data,
Yeah.
or like things that ChatGPT might be good at, like coding. There's like a solution, but in like public health or even health, like you don't have like a set solution. For example, you give people diagnosis, but that's probably just going to be like a probability that you are this diagnosis. So I was wondering, like, how much do you think that's gonna be a problem for the use of AI in this field, or how much is gonna, slow down the merging of AI into the field?
That's a great question. The best story I have about that is there's a story that is, I'm borrowing somebody else's story, so I'll give him credit. Ali Farhadi, who used to be the CEO of the Allen Institute for AI in Seattle, they were training an open source alternative to the big large language models like ChatGPT and Claude. And they kept having this problem that the models wouldn't converge. And they kept having this problem that they couldn't get the models converged, So they kept doing this sort of exploratory analysis to try to figure out why wasn't it working? Why wasn't the model converging to something they could use? And they found that there was a spike on one particular word. So there was a word that appeared very, very often in their training set, and it was the word beep. So they had an unbelievable amount of beeps in this data set. And so because of all the beeps in the training set, they couldn't get the models to converge. So they, of course, were curious and were like, why on earth are there all these beeps? So it turns out there's a subreddit that is dedicated to saying the word beep. And so people will just type literally in the subreddit, if you go there, it's just like beep, but repeated like many times. And so the training set was Reddit, and they had a gazillion beeps because like just this one subreddit had so many beeps in it. And so they had to go back and like process the data, get rid of the beeps, and be able to fit the model. The reason why I think that story is so instructive is in none of these fields, whether it's large language models or even the ImageNet example, is the data clean. It's always kind of ugly. Like the images, if you go look at the labeling on some of those ImageNet images, it's not as good as you would hope it would be. Like it doesn't always match what's in the actual image. It's not extensive. Like sometimes they're very short labels for something that like is very long. And so I think one of the things that's been really interesting, kind of being in having one foot in the two worlds, is we're unbelievably careful about the data that we collect in public health. And some of the things that have been enabled are because people are a little bit willing to go on a different trade-off on how accurate the data is versus how much they collect of it. And so not to say that we should stop caring about data quality, but certainly there's places on that curve of trade-off of how serious we are about every single data point versus having a huge collection. And we can be on that curve in various different places. So I think to answer your question really simply, I don't think that any data set that's kind of AI scale is going to be high quality, including in public health. And we would have to be willing to say, we're willing to give up the beep problem to allow us to have a big data set to answer these questions.
Hi, thank you so much for your presentation. I had a quick question about education and AI. So as far as, faculty here, I know students are absolutely using AI in many different ways, and I've seen kind of faculty integrate it in different ways. So sometimes they don't at all. Sometimes they go back to very old school ways of assessing, like Scantrons, or they try to integrate it in some way or assess it some way. So have you seen any good examples of how faculty have been able to give assessments to students, maybe integrating AI or working around cheating, quote unquote? I know we have very antiquated assessments like multiple choice or just like essays, which can be easily done with AI. So do you have any examples of how that's been done well for faculty who have kind of embraced AI?
Again, I don't know if I think Daniel had to go, but Daniel Obeng was telling me about how he's using it in the 620s here, and it sounded pretty cool. So I would talk to him. Okay. He probably knows more than me, first of all. But the interesting thing about the Scantron thing is the way, the way that a Scantron is scanned is with an AI model. It's like image recognition of that Scantron. So it's like we're going to Scantron to avoid cheating, but that's using AI to. So it's a little weird in my head. But I guess my feeling is it's sort of, again, I'm dating myself a little bit, but there was definitely a lot of math classes I took where they're like, you can't have a calculator. And, you have to do everything by hand. And like, they don't do that anymore. Like all the classes my kids take have calculators. Like that's just the way it works now. And I think that in some ways this is going to be like that. It's going to take a minute before it is like that. But I think at some point, everybody's going to use AI for exams. So, okay, so now you have to think, how do I redesign an exam so that you're testing what you want to test? And I think part of that is, what are you trying to test when you're giving somebody an exam? Is it a collection of facts? Is it how to calculate 18 times 23? Do you understand the fundamental concepts of what's happening here? And can you guide an answer and get an answer that's kind of has critical thinking to it? And that's harder for sure to design exams in that way. And so I don't think that's going to be an overnight thing, but at least my feeling is this is going to be a thing that's going to be part of everybody's lives, and we can fight it, or we can try to figure out a way to like reimagine what do we actually care about that they learn, given that they're going to have this tool. It's like, Google's still around. I'm still using Google, even though my teachers told me not to. So yeah.
Well, thank you.
Hi, I'm not a student. I'm actually on staff here.
Oh, great.
But I'm working on a capstone dealing with this. So my question is, how are you handling the issue of bias?
That's a great question. So one of the things so if you go back to the definition I use, there's data, algorithm, and interface. And any data is a reflection of our history. So in some sense, you're always collecting data about something that happened in the past. And so in that sense, you're always capturing all of the biases, all of the things that the world is doing to make that data be the way that it is. And so data is never a future looking thing. It's always a representation of history. And so you have to think about, if you're actually sort of trying to build something for the future, how do you capture the parts of our history that you don't want to be influential in the future and adjust for them? And so I think that there's bias in my mind is a huge component of all of this, has to be a part of the conversation. And I think the critical piece, I love that you're doing capstone. I love that you're not a student here in that sense, that like everyone should be a part of that conversation. It shouldn't be just the biostatisticians, the machine learning, like everyone has to be part of those conversations because it's going to influence all of us. And so I think, yes, bias is important. It's very hard to influence the bias in these big models like Anthropic, ChatGPT, et cetera, because they're costs $100 million, $200 million to train a model like that. And so how do we deal with the consequences of the fact that there are biases in those models is, I think, the right way to think about it, because there are going to be biases. And so how do we, knowing that that's going to be true, how do we deal with it in the world going forward? And then all of those companies are trying at the moment to try to like figure out how they're going to navigate this space. And I think you can be influential in certain ways and sitting on advisory boards and things like that for these companies as they try to figure out how do they capture and remove biases, because they are trying, but it's hard.
Okay.
It's an amazing question.
Thanks, Jeff. I'm Li Liu. I was actually on one of your slides.
I know. I was looking at my co-author the whole time.
Thank you so much. I have a question on data as well, but more on the ethical side. So with the AI, I think, actually I was talking to Joanne last Friday, probably the Friday before. There is these new rules about, for example, large publicly available data sets such as Enhance don't allow you to actually put micro level data into commercial available large language models. So I guess, I want to get your thoughts on how AI is changing the landscape of, ethics considerations, IRB reviews, but also, with your special, experience with not only just public health, but also biomedical data. What are some of the challenges or balances really that we are looking at and how to approach them?
It's a really good question. And when you become a chief data officer of a place, you think you're going to be like fitting models and building technology, and mostly you're going to be sitting in governance meetings and talking to lawyers, is what I've learned from being a chief data officer. And that's like a good thing, I think. Like in places where data is rightly regulated, like in healthcare, but also in other things like finance and other places, it's important that you put in place systems that enable you to protect those data while taking advantage of these. And so the mechanism that exists today with these companies is there's kind of two ways that you can protect data while interacting with these big models. One is, I think it was called Hop GPT. Hop GPT is like build a local version of these models, open source models, et cetera. Then you control where that data go kind of completely. Another way is you sign the right legal agreements and technical agreements with the company to essentially agree that they will protect your data and they won't train on your data and all that kind of stuff. Ultimately, I think both are good paths. If you have enough people that you can build your own Hop GPT, which is a place like this can do, but maybe a smaller place can't, that's one approach. And then the other approach is like what we're doing at the Fred Hutch, which is sort of trying to negotiate with multiple of these providers to get the right legal agreements in place and the right security perimeter in place so that if people want to upload data there, they know that they're not going to train on it. They know that they're going to, you kind of put protections in place to try to prevent those sorts of things from happening. So I think those are the two paths. And then really the bigger challenge is, okay, now you've uploaded that data to that system, even if it's not training on the data. What if it tells you to do something that's wrong? Who has liability? What if it tells you something super biased and somebody operates on that super biased response? Whose fault is that? There's a whole bunch of questions that we haven't even come close to answering yet as a society about those sorts of things that I think are coming at us like a truck. So we better get ready.
We're going to have to finish up. I saw Karen had her hand up.
Karen is the one that hired me here, so I think that she should get the last question.
We have previous chairs in the room, but I was guessing that Karen might have hired you, and like that.
She is.
That gives you that gives her the liberty.
That's right. She's the reason I was here.
Well, That was a wonderful talk, Jeff, first of all. But what worries me most about AI is the ability to tell what's false from what's true. And a lot of people have already, asked questions around this. If you have any reaction to that, generally fine. But the particular thing has to do about predicted data.
Yeah.
And so the truth of those predictions will have everything to do with the data that feed in
Yes.
to the prediction. And so is the field developing standards, around the quality of the data? What properties do those data need to have in order to generate predictions that are scientifically viable?
That's a great question. I will say that the answer to that is this area of research, in my view, is very recently developing. And so people are still trying to figure out even the basics of like, how do you make something work in this space? And no, they haven't really started talking about standards like that yet, but yes, they probably should. And so I think it's one of those questions where that's an amazing research question for a grad student to think about, which is what are the properties of a training set that would allow you to do this in a way that is healthy or right or whatever you want to call it, where you could trust the outcome. So I think that's one of the reasons you're seeing so much excitement in the statistical community is we took one spin at this problem, but there's a dozen other hard questions that nobody's answered yet that we need to figure out. So I think if you're a biostats grad student, this is a cool area to spend time in. Karen has good ideas, so you should go talk to her.
Thanks, Jeff. We appreciate it.
Thank you.
All right. And I think we're back to, here we are. Okay, we got to go up here. Okay. Thanks very much, Jeff. We really appreciate you sharing your insights and your enthusiasm. We have 28 abstracts, largely from our students, with a representation from faculty and staff as well. Many of the students and postdocs had a faculty representative, but the lead investigator was a student or postdoc. And we had members of our PHAISE task force review, and we have selected 3 winners. They get a $500 cash prize, and you get 5 minutes. I saw the slides. There seems to be more slides than minutes allowed. So we do want to have some time for some questions. We're going to do all 3 of the presenters. First is going to be Devious, who's going to talk about a machine learning approach to predict how to monitor or identify people who are speeding in South America. That's the postdoc award. From the student perspective, we're going to jump into autoimmune diseases and using how do you use a federated learning model to try to identify and unlock insights into disease. And we also have among staff, we have an approach that's going to try to use some agentic harnessing software to explore the scientific literature. So I think Devious, and I'm sorry if I'm Devious, here we go. We're going to have you come up and present yours. Oh, so it's Nicholas, but Nicholas isn't here?
Yeah, it's the same, Nicholas O. Davis.
Okay, well, Nicholas would have been easier.
Thank you so much.
Thanks.
Hi, everyone. Our work is about how to use AI to improve how the cities allocates enforcement to prevent road injuries. So as you may know, speeding is one of the major risk factors for road traffic injuries. As well, there are some kind of the strategies to prevent that, for example, enforcement, but most of the approaches are more to reactive approach. So for example, when there are a car accident, so we send the policemen over there, or maybe they say, oh, we can send, for example, enforcement randomly at different places to check if maybe there are some risk factor. But that creates some kind of the uncertainty because thinking, for example, you are a policymaker, secretary of the transportation, and you have to take the decision where I need or when I need to send enforcement. Hopefully we have a bunch of the data. So why not use that data to make some kind of the prediction? So we use like a case example, Bogota. This is a, a huge city in Bogota in Latin America, especially in Colombia. We have a nice feature to train our model. We train around 3 machine learning model, random forest, boots model, and also we use like a logistic regression, like the baseline. Usually it's good to practice. Our target variable was, or outcome variable was speeding, yes or no. So this is a classification task. So we got this nice result. I think are nice. The machine learning was around 80, 90%. That is good. Logistic regression was a little below, but the question is not just the performance of the model, it's what we can do it with that model. So as you can see here, for example, if we target, for example, the 20%, the highest risk vehicle, using machine model, we got around 50% of all of the overspeed. But if we use, for example, the standard way, for example, random allocation is around 20%. So we are increasing a lot of the performance, how we allocate the enforcement. But the question is not just how the model as well identify, is when and where. So using that, for example, you can see some example. In the column, we have the location, and the row, we have the time variable. The time variable here is, for example, the day of the week. If we, for example, see the first column, Monday, you can see, for example, we create a ratio of the overspeed. So the policymaker right now, or the stakeholder, have the decision, oh, Chapinero, Fontibon, and Tunjuelito, Monday have a high rate of the overspeed. Maybe I should send some kind of the information at that places. We run this analysis as well for the different time of the day. For example, morning, afternoon, at night, because we know there are different behavior associated. So the conclusion about this work is this kind of the approaches may improve the enforcement as well as maybe have cost effectiveness. And this is so important for a low and middle income country as well for high income country where we know there are resources constrained and also they have the potential to prevent injuries and save life. You are more than welcome to pass our poster and check a little bit more. Thank you.
Excellent job. You spoke quickly and kept on time. So Yixing Shin is a doctoral student in biostatistics, and it's going to talk about federated learning.
Hello, everyone. Sorry for standing between you and all the exciting posters. I'm Yixing. I'm a second-year PhD student in biostatistics, jointly advised by Dr. Jessie Tong and Dr. Isabel Stewart. And today, I'm excited to briefly go over this project we did last year, which is one of our federated learning framework designed for multi-center study on disease progression. First of all, this was motivated by a chronic autoimmune disease called scleroderma, or systematic sclerosis. It not only leads to the thickening of skins, but also a deterioration of multi-organ systems all over the body. And as one way to monitor its long-term progression, patients' % predicted forced vital capacity, or IVCs, are being regularly recorded at the clinics, thus contributing to our data. And there is high heterogeneity among these records that had to be carefully dealt with. For example, patients' different baseline starting point and rates of change, even under perfectly healthy conditions. On top of the patient level, we also have data from multiple sites. Currently, we are working with the Scleroderma Center from Johns Hopkins, University of Pittsburgh, and potentially more others. So this is essentially a 3-level longitudinal data set where patients are nested on the sites, and there are repeated measurements on their patients. There are site-to-site level differences, for example, sample sizes, testing devices, and the staff and the protocols of their data management. And this is where distributed research network can come into play, where we can benefit a lot from more resources and insights from our collaborating data partners than any single center study can provide. One major issue, however, with multi-center study like this is the data sharing constraint, particularly for a rare disease like scleroderma, which affects only 1 in every 10,000 people. Under the HIPAA laws, the sharing of individual participant data, or IPD, is highly restricted, which motivates federated learning approach to modeling without sharing any IPD. Formally, our PO stands for privacy-preserving efficient aggregation for longitudinal data. And broadly speaking, we designed PO to be such a general framework for multi-site EHR study so that it can go from the data pre-processing stage to statistical modeling and all the way to the downstream analysis. Some key properties of Pure are that it is both one-shot and lossless. One-shot meaning that we require only a single round of communication from each side to send summary statistic to the analysis center. And lossless meaning that Pure can produce exactly the same parameter estimate and inference as a pool data analysis, which here we implement with a mixed effect model. So what are the summary statistics we are transferring between sites? These are essentially components we use to reconstruct the likelihood function for our statistical model. Here, in the context of linear mixed effect model, these are some linear algebra cross products between all kinds of site level data. And all our summary statistics are thought to be privacy preserving in a way that they are usually a lower dimensional compression of the original data. And there are many 2-to-1 functions that can guard against any attempt to re-identify individual level records. We first apply Pure to just within the Hopkins cohort, where we do have IPD available. Here, the lossless property are being demonstrated here by our parameter estimate matching perfectly between Pure and the pool data analysis in terms of fixed effects, random effects, and residual variances. It is more exciting to actually deploy Pure to some real-world heterogeneous health systems, the Hopkins site and Pittsburgh site. The Hopkins site is arguably much larger and one of the oldest scleroderma centers in the country. It has a higher sample size and more diverse visual profiles. And the Pittsburgh site is slightly smaller, but when we first received the data, they have more severe patients coming in. So we successfully implemented Pure without touching any raw individual level records. It was able to identify clinically coherent risk factors of scleroderma as verified by our expert collaborators. Some key, the outcome FVC is significantly associated with some autoantibodies, although in different directions. It certainly affects African Americans much more severely than others. And although scleroderma is much more common among females than male, men actually experience a more severe disease course after onset. Speaking of the disease course, we were able to actually predict and plot out some long-term trajectories of FVC for different groups as based on the estimate of our mixed effect model. Although it seems like an eventual decline of lung function is inevitable, being in different risk group is certainly associated with different level of trajectories that you observe here. And this laid out some foundational work for more personalized treatment and medicine for scleroderma in the future. So just quickly sum it up. Hopefully I've convinced you that Pure is a significant step towards more efficient, trustworthy analysis across healthcare systems that are heterogeneous. If you're not convinced, talk to me at the poster session. It is a scalable, privacy-preserving, and lossless solution for researchers to consider. And there are always more biomarkers to consider, so we are moving on towards the multivariate settings of Pure. And there are hundreds more scleroderma centers and databases out there for us to build a stronger global consortiums for scleroderma studies. I want to thank all my collaborators here who are terrific clinicians and faculty who work together to make this and our future work possible. Thank you very much.
Thank you. Another excellent presentation. All of these posters will be you can circulate and ask your questions there. Elias Weston-Farber is our staff awardee to talk about open source agentic harness for literature analysis.
Thank you. All right. Hello, I'm Elias. I'm a senior cloud engineer for Metric in HPM. I work with Renan and Catherine, and I want to tell you a story about an ox. All right, so 8,500 years ago, humans domesticated the aurochs, this massive wild bovine. And for a long time, we really didn't know what to do with it. It gave us milk, meat, hides, but all that raw power, just standing in a field, eating your grain, staring at you. In 2020, OpenAI released GPT-3. It could write poetry, answer questions, generate code. Researchers were amazed. Everyone else had no idea it existed. The model was stuck in the AI lab, just like the ox. Eventually, someone tied a stick between two oxes' horns with a rope. It was crude. You could drag a log, barely. But for the first time, raw power was being aimed at a task. In late 2022, chat interfaces launched, ChatGPT, Claude, Bard. For the first time, anyone could talk to the model. No memory, no tools, no files. You type in, it types back. It was basically a rope tied to GPT-4, crude, but it worked, kind of. All right, here's where things get interesting. The plow was invented 6000 BCE. The ox was already domesticated, but for 2000 years, humans dragged the plow themselves while the ox stood 50 feet away. The tool existed, the power existed, nobody connected them. Models got more powerful, but people were still copying and pasting into models. Copying outputs, spreadsheets, manually feeding in documents into prompts, hand orchestrating everything. The plow and the ox were in the same field, not connected. All right, now we're getting somewhere. Around 4000 BCE, someone built a proper yoke, a shaped beam that sat on the ox's shoulders and connected it to the plow. Productivity exploded, surplus food, cities, trade routes, civilization. Right now, in 2025 and 2026, we are building the yoke for AI. In AI, we call it a harness. Any software that connects the model's raw intelligence to real-world tasks. It might manage tools, coordinate multiple models, or enforce a structured workflow. The model is the ox, the harness is the yoke, and the yoke is what turns power into useful work. Model plus harness equals agent. All right, and it's already scaling. Farmers figured out you could yoke multiple pairs of oxen together for heavier loads, 12 oxen pulling a 10-ton wagon. The key lesson from ox pulling competitions, a coordinated team of smaller oxen consistently beat a larger, stronger pair that was out of sync. Coordination beats raw power. That's exactly what's happening in AI. Multi-agent systems where a fast model handles triage and powerful models handles reasonings are outperforming single models working alone. It's not about the biggest ox, it's about the best harness. All right, so then and it's not theoretical. 4 MIT grads built Cursor, an AI coding tool. They trained 0 models at the time. They built the harness that connects existing models to where coding actually happens. It's now worth $29 billion, the fastest growing B2B company in history. The ox breeders, OpenAI, Google, Anthropic, are now investing in the Yo company. Even the people building models are betting the harness is what matters. So here's my question. If coding harnesses make models dramatically better at coding, shouldn't we be building scientific harnesses? Because here's the thing. These coding agents are already doing work that looks really good. And general purpose tools are getting more capable every month. If we in public health and science don't build our own harnesses, ones designed for our workflows, our standards of evidence, our need for reproducibility, someone else will, and they won't understand what rigor means in our context. That's what I've been working on. Science AI is an open source harness for systematic literature analysis. You give it papers and a research question, it creates specialist agents, extracts structured data, tags every value with the exact source quote and page it came from. To see if that actually works, we gave 3 different AI models, GPT, Claude, and Gemini, then 19 source papers from a published meta-analysis on smoking and bone healing. No forest plots, no original study assignments, just the papers and the methods, and we asked, can you reproduce the published results? All 3 models recovered the primary finding, that smoking roughly doubles the risk of fracture non-union, or like not healing. They converged on some secondary outcomes too, but they also disagreed with each other, not just on numbers they extracted from the same papers, but on methodological decisions. Which studies were relevant to each outcome, how to classify an exposure group, what counts as a case, the kinds of judgment calls that define a systematic review. That's exactly the kind of thing we need to understand better. The results look promising, but the field doesn't yet have agreed upon benchmark data sets designed for scoring AI on these tasks, not just extraction accuracy, but the quality of those methodological decisions. The reference data is out there, but it's not set up for this kind of testing. Building those benchmarks is part of the work ahead, especially if you're an AI skeptic. Help make benchmarks to prove AI can't do it. This is an invitation. This isn't a pitch for my software, it's an invitation. We scientists, public health researchers should be the ones building and evaluating these tools. Not waiting for a tech company to hand us something and trusting it because the output looks polished. We should be driving the ox, not the other way around. If you want to dig into how this works, come find me at the poster session. I'd love to talk about how we can build and benchmark this together. Thank you very much.
Thanks very much. And I don't think we have time for questions. But those were great presentations. One more time, Let's congratulate our staff, student, and postdoc awardees. And we are, let's go down. I think we have some summaries of the posters that we have included. So we got a range of different topics, policy and decision-making, some clinical or epi applications are pretty well represented, some geospatial approaches, and communications, human interaction. So we cover a wide range of topics. I think it's illustrative of the type of activities that are ongoing around the school. So please go ask questions of the speakers. Jeff will be circulating around. You can follow up and ask him some additional questions. Meet your PHAISE task force member. Learn a little bit about AI and public health, make some connections, and develop a new collaboration. You can also have some food. So thanks once again to Jeff. Thank you for participating. Enjoy the posters.